Section: Introduction. In this section, we will discuss the advancements made by large language models, LLMs, in various language tasks but their limited exploration in spatial reasoning. Spatial reasoning is crucial for human cognition as it enables us to understand and interact with our surroundings, involving tasks like comprehending spatial relationships between objects and their movements. While LLMs excel in reasoning tasks like math and common sense, their spatial reasoning abilities are not well understood. Humans can go beyond verbal reasoning and create mental images from visual input, allowing them to imagine scenes mentally. This ability, known as mental imagery, plays a significant role in spatial reasoning tasks like navigation and mental simulation. Inspired by human cognitive functions, we believe that LLMs might have the capacity to create and manipulate mental images for spatial reasoning. To test this hypothesis, we introduce the visualization of thought (VOT) prompting method to enhance LLM's spatial reasoning abilities. This method involves incorporating a visual spatial sketchpad into LLMs to visualize their reasoning steps. By using zero-shot prompting, LLMs can generate mental images without prior demonstrations or text-to-image conversions. We conducted experiments on tasks like natural language navigation, visual navigation, and visual tiling to evaluate the effectiveness of VOT in enhancing LLM's spatial reasoning. Our findings show that VOT prompting consistently improves LLM's performance on these tasks by encouraging them to visualize their reasoning steps. Our contributions include shedding light on LLM's mental imagery for spatial reasoning, developing tasks like visual navigation and visual tiling with synthetic datasets, and proposing the VOT prompting method. Through empirical evaluations, we demonstrate the effectiveness of VOT in enhancing LLM's spatial reasoning abilities compared to other methods and existing models. This suggests that leveraging mental imagery akin to the human mind's eye process could be beneficial for improving LLM's spatial reasoning capabilities. Section Summary. In this section, we explore the spatial reasoning abilities of large language models, LLMs, and propose the visualization of thought, VOT, prompting method to enhance their spatial awareness. We investigate how LLMs can create and manipulate mental images for spatial reasoning tasks, such as natural language navigation and visual tiling, aiming to emulate human-like multisensory perception. By augmenting LLMs with a visual spatial sketchpad through VOT prompting, we observe significant performance improvements in spatial reasoning tasks, shedding light on the potential of leveraging mental imagery in machine learning models for enhanced spatial understanding. Section: Natural language navigation. In this section, we explore natural language navigation, which involves moving through a spatial structure by taking random steps to recognize previously visited places. This idea is inspired by how humans navigate mentally. Understanding loop closure is crucial for this type of navigation. We define a square map using a series of random walk instructions paired with objects. Our goal is to correctly identify the object at a given location based on a sequence of navigation instructions. We then move on to visual navigation, where a model is challenged to move through a 2D grid world using visual cues. The model needs to generate instructions to navigate in 4 directions while avoiding obstacles. This task involves route planning and predicting the next step, requiring spatial reasoning. In the formulation, we describe how to generate directions for moving through a grid map from a starting point to a destination. The model needs to predict the correct direction for the next step based on the map and previous instructions. The implementation involves creating question and answer instances for each map and set of navigation instructions. The underlying graph of the navigation map follows a specific pattern, and multiple QA instances are generated for evaluation. Visual tiling extends spatial reasoning challenges by testing the model's ability to work with shapes in a confined area. The task involves selecting the right shape variant to solve a puzzle within a rectangle filled with different shapes. We introduce visualization of thought, VOT, prompting to enhance spatial reasoning by visualizing intermediate steps. This approach generates reasoning traces and visualizations to aid in decision-making. The visual state tracking allows for deriving subsequent states, improving the model's spatial reasoning abilities in a grounded context. Section Summary. In this section, we explore the concept of natural language navigation, inspired by human cognition and involving random walks to recognize locations. We delve into visual navigation tasks in a 2D grid world, focusing on route planning and next step prediction. Additionally, we introduce visual tiling challenges and visualization of thought prompting to enhance spatial reasoning skills in LLMs through interleaved reasoning traces and visualizations. Section: Experiment. In this section, we conducted experiments with a multimodal model for visual tasks that have an image corresponding to each text input. We used GPT-4 and GPT-4 Vision via Azure OpenAI API, which are advanced language models. We set the API parameters to temperature 0 for greedy decoding and top P1, with model versions 11.06 Preview and Vision Preview. We used zero-shot prompting for all experiments. Depending on whether the language model is prompted to visualize intermediate steps, we tried 3 settings: GPT-4 COT, GPT-4 with OVIZ, and GPT-4 VOT. We also tested GPT-4 Vision with counterpart image input as GPT-4 VCOT. The prompts for each setting were specific to guide the model in its reasoning process. We ensured a fair comparison among all settings within the same task. For the natural language navigation task, we created 200 square maps with 9 landmarks in snake order traversal and a set of navigation instructions. In visual navigation, we observed that the number of generated maps is slightly lower than 2k+1, as the navigating step k increases. In visual tiling, we generated various configurations to fill a 5x4 rectangle with 5 polyomino pieces and created QA instances for each masked piece. To evaluate the models, we extracted answers from the model output using pattern matching. We calculated accuracy for most tasks using a specific equation. For route planning, we normalized the navigation instructions and measured the completing rate against the ground truth navigation instructions. We reported 2 metrics for the dataset of N maps: average completing rate and success rate. Our results showed that GPT-4 VOT performed significantly better than other settings across all tasks. The visual state tracking in GPT-4 VOT proved to be effective in interpreting actions within a grounded world. In the natural language navigation task, GPT-4 VOT outperformed GPT-4 with OVIZ by 27%. In visual tasks, the performance gap between GPT-4 COT and GPT-4 VCOT suggested that a language model grounded with a 2D grid could excel in spatial reasoning tasks. However, GPT-4 VOT still had room for improvement, especially in challenging tasks like route planning. In our discussions, we highlighted the importance of visual state tracking in GPT-4 VOT. We observed instances where visual state tracking failed and compared it with the reasoning patterns of GPT-4 COT. We also noted incorrect visualizations in the model outputs. We raised questions about how different prompting methods affect visual state tracking behaviors and how visualizations contribute to final answers. Further analysis of model outputs across all tasks and case studies were provided for interested readers. Section Summary. In this section, we experiment with a multimodal model using GPT-4 and GPT-4 Vision for visual tasks, employing various prompting methods like GPT-4 COT and GPT-4 VOT. We conduct tasks such as natural language navigation, visual navigation, and visual tiling, evaluating model performance based on completion rates and success rates. Results show that GPT-4 VOT outperforms other settings, indicating the importance of visual state tracking for LLMs in interpreting actions within a grounded world, though challenges remain in tasks like route planning where LLM performance drops as complexity increases. Section: Do visual state tracking behaviors differ among prompting methods? In this section, we examine whether visual state tracking behaviors differ depending on the prompting methods. For each model output, we look at the sequence of visualizations sampled before the final answer is generated. We then compare the length of this visualization sequence, L_V, with the number of reasoning steps, L_S. We calculate complete tracking by checking if the length of the visualization sequence matches the number of reasoning steps for each state, and partial tracking by seeing if there is at least one visualization before the final answer is generated. The results show significant differences between these settings. In the case of GPT-4 COT without explicit visualization prompts, we observe a high tracking rate across most tasks, except for route planning. This suggests that LLMs naturally have the ability to track visual states when spatiotemporal simulation is needed for reasoning. Additionally, the gap between visual tasks and natural language tasks indicates that 2D grid input is more likely to activate this innate capability than natural language. Visual state tracking behavior is influenced by prompts to different extents. For example, when reasoning is removed from the prompt of VOT, visualizations are sampled after GPT-4 generates the wrong answer. By explicitly prompting LLMs to visualize their reasoning traces, VOT significantly increases the visual tracking rate, thereby improving performance. The ability for visual tracking may stem from tasks involving tabular data, city grid navigation, maze exploration, and coding problems. These tasks require understanding and manipulating objects in a 2D square grid. Exposure to ASCII art comments during LLM's code pre-training may enhance this ability by requiring them to generate mental images and text sequences, improving spatial visualization and spatiotemporal causality. In tasks like natural language navigation, prompting GPT-4 with "use ASCII art to visualize" significantly boosts the tracking rate and task performance. This suggests that visualizations play a crucial role in enhancing final answers by aiding in spatial visualization and understanding. Overall, while there is room for improvement in the accuracy of state visualization, LLMs show promising capabilities in multi-hop visualization tasks that adhere to spatial constraints. The accuracy of spatial understanding is relatively high, ensuring correct decision-making based on accurate visualization of internal states, leading to improved performance. However, in tasks where LLMs can rely on logical reasoning without visualizing internal states, VOT prompting may underperform. For instance, in experiments involving natural language navigation within a ring, GPT-4 COT outperforms GPT-4 VOT, indicating that visual prompts may not always be necessary for certain tasks. Section Summary. In this section, we analyze whether visual state tracking behaviors differ across prompting methods. We compare the sequence length of visualizations with the number of reasoning steps and observe significant differences in tracking rates among different settings. Visualizations play a crucial role in enhancing final answers by boosting spatial visualization and spatial understanding capabilities of large language models, LLMs, although improvements are needed for accurate state visualization. Section: Case Study. In this section, we explore a case study where we examine visual state tracking similar to spatiotemporal simulation. Throughout our investigation, we observed various behaviors of LLM. Firstly, we noticed that there were nearly 30 different symbols used in navigation tasks to track progress, such as marking the path and current location. Interestingly, LLM successfully used directional arrow emojis in challenging cases to show both location and moving direction at each step. Secondly, we found inconsistencies between the language instructions and visualizations generated by LLM across all tasks. Sometimes, LLM provided accurate language instructions but inaccurate visualizations due to limited capabilities. In other cases, LLM generated incorrect answers even when the visualization was correct, indicating limitations in spatial understanding. Lastly, we identified a self-refinement mechanism in visual tiling tasks where LLM experienced spatial hallucinations due to inconsistent or inaccurate visualizations. However, LLM refined its reasoning process, leading to accurate visualizations and corrected final answers. These findings highlight the importance of spatial reasoning and language understanding in natural language processing, particularly in the context of large language models like LLMs.